In the previous video, I discussed the essential components of a C program and the three main steps involved in turning source code into an executable file, namely pre-processing, compiling, and linking. In this, the last video in the series, I'll take you through the practical steps of compiling a C program. I'll also show you how you can get data from the user as arguments passed to main, introduce you to C's custom data type manufacturing facilities, and introduce you to dynamic memory allocation. I'll end with a roundup of other aspects of C coding that you can easily learn on your own. To make a complete executable program with C, you'll need to install a compiler and some other tools. You'll often hear these tools called a development environment, or DE. This is to distinguish it from the live environment, that is, the computer system environment in which the finished program is to be ultimately deployed. If your newly created or modified software made in the development environment is designed to run some critical infrastructure, then it won't immediately be deployed from the development environment to the live environment. Instead, it'll be deployed to an intermediate environment designed for rigorous testing by simulating aspects of the live environment. This is called a staging environment. At its most basic level, a development environment is composed of a text editor to write your source code and a C compiler. All C compilers I know of will come bundled with the preprocessor and linker programs as one package, so there's no need to look for those separately. If all the development environment tools can be operated by and provide user feedback via a unified user interface, this is called an integrated development environment, or IDE. And IDEs often include additional features to assist productivity and debugging. Some example IDEs include the free and open source code blocks system that is available for Linux, Windows, and macOS. Another example is Microsoft Visual Studio, which is not open source but has a version which you can use without paying money under the terms of a restrictive Microsoft license. There are advantages and limitations to each IDE depending on your needs. Some disadvantages of using a closed-source commercial solution are that it may be difficult to port your software to other operating systems. You may face restrictions on what you are allowed by license to do with your software, and you may not be able to update or edit your program in the future without using the latest version of the same company's IDE and license, which may no longer be free and or may have even more restrictions imposed. For all these reasons, for my scientific work, I prefer to use free and open source cross-platform solutions. For the purposes of my demonstrations, I'll be using a very simple development environment which consists in a text editor called Geany and the GCC compiler, which stands for the GNU Compiler Collection. It is possible to link GCC to Geany to create an IDE, but I won't be doing that here. I'll just be using the command line interface to run the compiler and the compiled programs. There are many videos and guides on how to install these on common operating systems, so I won't duplicate that here. Instead, I'll give you some general pointers and put links in the video description to sites with more detail. Most Linux distributions come with GCC pre-installed. To check if you have it, just open a terminal and type gcc --version and hit return. If you see something like this, then you know GCC is installed. Otherwise, just install it using your distro's installation package management tool. For Microsoft Windows users, you won't normally have GCC installed. You can install it using the MSys2 development environment by following the instructions on their website. On macOS, the default compiler is called Clang, and if you type GCC on your command prompt, your system will actually run Clang, not GCC. GCC can be installed using a program called Homebrew, which you need to install first. You may then need to adjust symbolic links to ensure that when you type GCC, it actually runs GCC. Now that you have your compiler, you'll need something to write your source code with. Any plain text editor will do, but Geany provides additional features useful for writing programs, like color-coded text and much more. For Linux, you can usually install Geany using your package manager. For Windows, download the setup.exe installer from the Geany website and run it as administrator. For macOS, download the DMG file from the Geany website, Double-click the DMG file to show its content, then drag the application from the DMG window into the applications directory to install, and you may need an admin password to do this. So now we're all set up, let's test this all works by starting Geany and writing a program. Traditionally, the first full program you're taught in any new high-level programming language is a program to print the words "Hello World" somewhere on an output device. C has no intrinsic high-level facilities to do input and output with any peripherals. It only allows for reading and writing bit patterns to and from memory addresses. So, to simply print the words "Hello World" to the screen would require you to know detailed machine specifications, like what are the memory addresses of the graphics card screen buffer, and what are the control register addresses that trigger the transfer of the contents of that buffer to the display driver, etc. However, most C compilers come with a set of standard function libraries that do all this hard work in the background, and they package it up for you in neat user-friendly functions. One of these is called the Standard Input-Output Library, stdio. We can use those standard I/O functions so long as we include their prototype declarations in our program. I'll use the preprocessor #include directive to include the header file for this I/O library, as was discussed in the previous video. So, now that we've got access to convenient I/O functions, we can write the main function. I'll begin with the declaration of main and its arguments and open the function's code block. I'll explain how to use the arguments to main later in the video. And now we'll use the printf function, which stands for print formatted, and pass to it as an argument a string constant that has the text we want to print. The \n at the end here is the escape sequence for a new line character, which means the terminal cursor won't stay on the same line when the program exits, but will appear at the line beneath it. If that's not clear, then try compiling the program without the /n and see the difference when you run it. The function main is of data type int, so we must end the function by returning an int value. It's customary to return 0 if all went well and some non-zero number if there was an error. So, since we're not doing error checking here, we'll assume all went well and just put return 0. So that's the program completed. Let's save this with the name hello.c. The .c extension is the usual way we mark a C source code file. For this example, I've saved it in my home directory. Now let's compile and run it. Bring up your command prompt and ensure your current working directory is the same as where the hello.c file is. On Windows MSys2, the command prompt for GCC is the program called ucrt64.exe. So double-click that to bring up the correct command prompt. Then simply type gcc space hello.c space -o space hello and hit return. And here we see the object file that contains the executable machine code. It also contains some other stuff, such as formatting necessary for the operating system to identify it as an executable file and pass it to the machine for execution, but I won't go into the details of the machine-specific formatting of executable files here. Note that we used functions from the standard I/O library, but we did not need to write any specific linker commands, because the default behavior of the GCC compiler is to automatically link with some of the standard library functions. On many Linux and Unix systems, before running a program, you first need to give the object file executable permissions. You do that with the chmod command, like so. However, with MSys2 on Windows, GCC creates a native Windows exe file with a .exe extension, even though you did not specify an extension in your compile command. You do not need to do any chmod command for this exe. In this respect, MSys2 differs from true NIX systems like Linux and Mac OS. Now you can run the program by typing its name and press return, like so. And there is the result, as expected. Note that I needed to put the / in front of the program to tell the command line interpreter that the program I wanted to run is the one in the current directory. The current directory is signified by the /. Without this, the interpreter will look for a program called hello in the search directories listed in your path environment variable and won't find it there, so it will complain, like this. So, the // is needed unless your executable program is placed in one of the folders listed in your path environment variable. If these concepts are unclear to you, you should spend some time researching how to use the Linux command line. The msys2 command shell on Windows and the command window on macOS are similar. The function main takes two arguments, an integer called argc and an array of pointers to car called argv. When you run a program from the command line by typing its name, you are effectively getting the operating system to call the main function of your program. Any characters you type on the command line before hitting the return button will be passed by the operating system as arguments to main in the form of a series of character strings separated by whitespace, like this. All arguments received by main from the command line are treated as character strings, and this includes numbers. So this value here, for example, will be treated like a string constant, like this. The argc argument of main stands for argument count, and its value will be the total number of strings you provided on the command line. This includes the actual name of the program, so in this example, argc will be 5. The argv argument of main stands for argument vector, which is just a fancy way of describing the array of character pointers, which you can think of as an array of strings, because each member of the array will point to the address of the beginning of each string in your argument list. When calling a program from the command line, the very first element in the list, argv0, will point to the name of the program as you typed it on the command line. So, in this example, it will be hello. The simple hello.c program we wrote does not actually use these arguments, but we can easily modify the program to print a list of all supplied arguments using the special formatting abilities of the printf function and a conditional loop facility of C called the for loop. To do this, let's go back to our hello.c source program and add an index integer variable called idx. Now we'll add a line to print the value of the argc variable, like this. In this case, %d is a special formatting character that tells printf to replace the %d with the actual value of an integer number you must supply as another argument over here. There are many different formatting characters and rules that can be used with the printf function, and you can read about them in the Kernighan and Ritchie C book or other free online references. Now we'll execute the following block of code a number of times. How many times will depend on some conditions. Those conditions will be set out using the conditional for statement like this. The for condition takes 3 statements. The first does any one-off initializations before entering the code block. Here I initialize the idx variable to 0. The second statement is the conditional test, and it is like an if statement. Here, the code block will only be run if the value of idx is less than the value of argc. Finally, we have a statement which is executed each time the code block is run. In this case, I'm simply incrementing the value of idx by 1. So this block of code will be executed again and again until the value of idx increases to the point where it becomes equal to or greater than argc. If argc were 0, then this block of code will never be executed, not even once, because this condition will never be satisfied. So the program will just skip this block and move on. So now we fill in the code of this block, and I'll again use the printf function, but this time with 2 formatting characters. The first is the %d I used before, which, you know, will be replaced by an integer number. Next, I'll use the %s formatting character, which printf will replace with a string. So now we must supply the actual variables whose values are to be substituted for those formatting characters. The first is the integer, which will be the value of idx. The next must be a pointer to the beginning of a character string, and this will be the idxth pointer in our argv array of pointers. So this program will list for us all the argument strings we supplied on the command line, each on a separate line. Let's save this and compile it as before. And when we run it, we get this. So this shows you how the user can communicate data to your program when they run it, and how you can access that data in your C program. There are other ways of getting information from a user while your program is running. Some of these involve functions called scanf or getC or getCar. But I'll leave it as an exercise for you to read up on those functions, because you should have enough knowledge by now to do that. I'll put some links in the video description to get you started. Another way to get information from your user is to read in a file, like a text file or an image file, from somewhere on the file system, and use the information stored in that file as input data to your program. A common way to read a file involves using a file pointer variable declared like this. You'll know from your general understanding of C syntax that a variable we choose to call fp is being declared as a pointer to a data type called file. But what is this file data type? It's not an int or a char or a float or a double, none of the standard basic data types I've taught you about in the previous videos. So how many other data types are there in the C programming language? Well, the answer to that question is as many as you like. C has facilities that allow you to define your own custom data types. These new data types may range from a simple renaming of an existing data type to some compound data type made up of several existing data types. The Typedef facility is used to rebrand a data type. It gives an existing data type a new name that will make its use in a program easier to follow for a human reader or programmer. For example, we can rebrand the float data type as a data type called dimension, like this. Then we can use this new dimension data type when specifying variables that are intended to hold the height or width or depth of something, like a rectangle. A typedef does not delete or remove the original name for the data type. We can still use the original name if we want, such as in this example. Typedefs are just a rebranding tool. However, we can also make new data types from combinations of existing data types using a facility called a structure. This allows you to keep information in variables of various data types all together in a unit that can be treated as a single data type. A structure is defined by the word struct, followed by an optional name tag, followed by the actual components of the structure between two braces. I'll go into the specifics about what goes in between the braces shortly, but first note the general form of a structure declaration in this example. The new data type is the part from struct to the end of the braces. The equivalent form for a standard data type like the double would be like this. The tag is an optional name label that you can use to refer to that particular structure data type later in your code. This is useful if you don't want to declare all the variables having that structure data type immediately. So you can do something like this. Note that you need to put struct in front of the tag, rectangle in this example, when you actually come to declaring variables using that structure. But you don't repeat the structure contents between the braces. So now, what do the contents of the braces look like in a real structure definition? Let's continue with this rectangle structure example. If I want a new data type to use for sorting and manipulating rectangles, I might want this new data type to be able to store the coordinates of the top left of a rectangle, and I would want it also to store the height and width of the rectangle. Let's assume the coordinates need to be integers, but the height and width can be any fractional number, so these can be floats. With these requirements, I could then define my rectangle structure like this. So now we can use it in a program like this, and we access the members of a structure with the dot operator like this. We can also use typedefs inside structure definitions, so we could have defined our rectangle structure like this. And also, because structures are just data types, we can use typedefs for them as well, as with this example. So here we define our struct without a tag and give the typedef of our struct the name rect. This rect label will include the struct bit, so there is no need to use the struct keyword when we declare variables using this typedef, like myrect1, myrect2, and the array of 12 rect structures rectlist in this example. Structures can also contain other structures within them as members, like this. And in your code you would access the members of the top left structure within the rectangle structure like this. Just as we have pointers to the standard data types, so we can also declare pointers to structs like this. We can use the ordinary star operator to dereference structure members, but because of the compound and possibly nested architecture of structs, you need to use brackets to get the syntax right, and it's easy to make mistakes. so a special syntax is available and more commonly used to dereference elements within a pointer to a struct by means of the arrow operator, like this. There are additional rules, possibilities, and limitations with structs. For more on this, consult the Kernighan and Ritchie book or other online resources. And so now, to answer the question posed at the end of the previous section, what is this file data type? Well, it's just a typedef of a structure that contains all the data types and variables needed for the compiler to handle access to a file, and this structure and typedef are defined in the stdio.h header and library file. Finally, a quick word on unions. Unions have a similar syntax to structs, so may be confused for them. They are actually quite different. A union is a memory saving device, whereby a single block of memory can be allocated to store any one of a number of different data types. Unlike a structure, only one of those data types can be used at any one time, because they all share the same memory block. I don't use unions much in my image processing work, so I won't go into the details, but the Kernighan and Ritchie book and other online resources explain them more fully. I discussed in a previous video how you can declare an array of a certain data type to get a bundle of those variables that you can access via an index in square brackets like this. In this example, the compiler will allocate just enough memory to store 25 unsigned car values, and the name I gave the array suggests that I'll use it to store pixel intensity values, perhaps for an image that is 5 pixels high and 5 pixels wide. But what if you don't know, in advance of compilation, how many values you need space for? For example, what if your program is to read the values from an image file on disk, and that image could have any dimensions? You could just guess at a maximum value, but that could be too many for some images and so wasteful of memory. Or it could be too little for others, and your program might crash with a segmentation fault if you try to load in more pixel values than you allocated storage for. The answer to this is to use dynamic memory allocation to a pointer instead, as shown in this example. Here, myPixels is a pointer to unsigned car. Then, after your program reads the image file and discovers the required number of pixels, you use the standard library function malloc to allocate exactly the required amount of memory to the pointer, which you can then use as a standard array, but with extra benefits, some of which were described in my previous video on pointers and arrays. When you allocate memory dynamically like this, your program keeps hold of that memory till either the program ends or you deliberately release the memory using the free function, as shown. If you don't free up this memory as soon as you no longer need it, your program could end up hogging a lot of the system memory after a while, and this will prevent your or other programs from running or make them run slowly due to the need to use virtual memory. A program that accumulates memory that it no longer needs in this way is said to have a memory leak. So, you should always get in the habit of freeing any dynamically allocated memory you get as soon as you finish using it. There are other related dynamic memory allocation functions like calloc and realloc, and you should read up about those in the Kernighan and Ritchie book or other online resources. Although in future videos I'll be showing you C source code examples, this is the last in my series of videos dedicated to teaching C programming. There are many other key words and standard library functions in C and many rules that cover default behaviors in otherwise ambiguous situations. I don't intend to make videos to cover all that because there are many good videos and reference texts out there, and if you've followed my C programming videos up to this point, you'll have learned all the general principles you need to teach yourself the rest of what is essentially just coding. In order to understand the source code of my programs in future tutorials, you should make sure you are familiar with the keywords and coding principles shown in this slide as a minimum. In summary, a minimal development environment, or DE, consists in a text editor and a compiler. The open-source GCC toolchain and Geany text editor form a cross-platform development environment. Many others are available and may be more appropriate for your specific programming needs. You can receive input data to your main function via command-line arguments using argc and argv, as well as by reading in files and using other functions like scanf. You can define custom data types using structures, unions, and typedefs. when you dynamically allocate memory, ensure you always free it to avoid memory leaks. Future videos will concentrate on practical applications of C for making simulations and for image processing, but I hope you found this series of 6 videos helpful in learning and understanding the C programming language. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.